we are going to start section 3.1 now. Okay, we are done with chapter 2. In section 3.1, the first thing that I'm going to do is define a bunch of terminologies, and then we'll see some examples. So let's let f be defined on a set D of real numbers. We say that f has an absolute maximum on D if there exists C in D such that f of C is larger than f of x for all x inside of D. So what we are saying is that f has an absolute maximum on the set D if there is a C inside of D such that f of C is the largest value of f on D. Okay, f of C is the largest value of f on D. Define well, f of C here, f of C is called the absolute maximum value of f on D. So how would you define absolute minimum? If I want to define absolute minimum, what will change in my definition? So I have to reverse the inequality. So f of C will be the least value of f on D. So let me just say the absolute minimum value of f on D is defined in a similar way. Okay. Now, along with the idea of having an absolute maximum value and absolute minimum value, we also have the idea of local maximum and local minimum value. Yeah. Let me know when you're done. Okay, next we say that suppose that well, let me just say it this way, f has a local maximum value at C if f of C is the largest value of f on an interval open interval centered at C. So f has a local max at C. It means that around C there is an open interval, so that f of C is the largest value of f in that interval. Okay. And similarly, we define local minimum. So a local minimum of f is defined similarly. Together, local max and local min are called local extrema. Okay. So together they are called local extrema. The absolute max and absolute mean, they are called the extreme values, or the extremas. Okay. So there is a reason. If you have a function f, it has only one absolute max and one absolute mean value. Okay. But a function may have more than one local max or a local mean. Okay. So we're going to see a bunch of examples to explain these definitions. My first example would be a general one. So let's say I have my x-axis, my y-axis, and let's consider the following curve. Let's say okay, so let's say these 2 points here is A and B. So let's say this is the graph of some function f of x, and x is between A and B. So in this example, I am going to let this point here, I'm going to name that alpha 1. Going to name this one alpha 2. Okay. This one at 0, I'm going to call that beta 1. Okay, beta 1 is in my picture, that's 0. And and I have beta 2 right here. Okay, and you know what, let me call this beta 1, let's call this beta 2, call it beta 3. So in my picture, what is the absolute maximum value? The absolute maximum value is the value of the height of the curve at what? Beta 2, right? 0. And what is the absolute minimum value? F of f evaluated at alpha 2. And notice now, what are the local max and local mean values? If I look at this point here, right, this point, if I pick a very small open interval centered at beta 1, wouldn't you say that f of beta 1 is the largest value of f in that interval, right? So that point, at that point I have a local maximum. And similarly, if you now look at this point here, this green point, and think about a small open interval centered at alpha 1, notice that f of alpha 1 is the least value of f in that interval, right? So so f of alpha 1, that's a local minimum, okay? And similarly, I also have a local minimum here. Incidentally, that's also the least value, that's also the absolute minimum, right? So at alpha 2, I have a local minimum as well, by definition, okay? But I also have that, I have the absolute minimum there, okay? At this point, I have the absolute maximum, as you said, but I also have a local maximum there, okay? How about this? How about this point here? This point here? This point here, I have a local max as well, right? Because if I pick a very small interval centered at beta 3, that's the largest value of f there, okay? Is everybody okay? Is it clear what we are trying to define here? Okay. Okay, that's very good. Say it again. So yeah, so let me write that down. Local max, alpha 1, alpha 2, and alpha 1 and alpha 2 I have local min. Beta 1, beta 2, beta 3 I have local max, okay? So let me write that down. Local max at beta 1, beta 2, beta 3, and local min at alpha 1 and alpha 2. Okay?
So if you're absolute min or absolute maximum, they're also considered local.
Oh yes, yeah. Unless okay, so let me, since you asked me that question, unless this happens, okay, so let me give you another example here. What if I have, let's consider the function f of x equals to x squared, okay? But I am going to only look at the domain between -1 and 2, okay? So let's see what's going on with this function. So let's say this is my x-axis, my y-axis, and let's say the graph looks like the following. So this is where I have 2. This is where I have -1, okay? And let's say, well, that's the graph of x squared, okay? So what's the absolute maximum now? The absolute maximum value So absolute max on the interval from -1 to 2, right? On this interval, what's the absolute max? Is basically f of 2, right? But then f of 2 is not a local max anymore. Why? Because if I want to pick if I pick a small interval around 2, that's not the largest. I mean, I cannot pick points on the right hand side. Okay. Is that making sense?
Wait, so it's not what?
Local max. It's the absolute max.
The absolute, it's not the local.
Yeah.
Because it doesn't have anything at.
On the right of 2. Okay. Okay, so that's just a conversion I'm taking. It's if I say, well, as long as it's in a interval, it's the highest value. I'm going to call it local max. I can do that, but for local max, I just want to take something that's where you have points on both sides. Okay.
So what about when you have that the graph above this? When the local.
Yeah,
it would be.
So note that I didn't say I have a local max at A or.
I was just going to say, what about
local.
A and B?
Yeah, at A and B, I don't have.
Not local, but.
I don't have.
Absolute.
No, because absolute there is only one, right?
If you have brackets on either side, when you pick that small point.
Oh, right here.
Yeah.
If I have points here.
Right.
Yeah, but if I have points here, then it might not be lower anymore, right? Maybe the graph goes this way or goes this way.
But could it be an absolute?
Oh, I might have an absolute value at the end point. Is that what you're saying?
Yeah. That's what I'm asking.
If I have an endpoint, that's why we are doing this example. I'm saying that at 2, I have an absolute maximum. It's just not a local maximum. Yep. So here I have, what's the absolute minimum in this case? Yeah, in this case, the absolute minimum would be the value of f at 0, which is 0, as you said. Now, let's change the question and say, can you say, what's the, if I say, what's the absolute max of the function f of x equals to x squared on the interval from -infinity to +infinity, and what's the absolute minimum of f on the same interval? What did you say now? Yeah, there isn't any absolute maximum, right? Because in this case the graph goes up forever. There is not a single value which is bigger than all the other values, right? And in the but it still has a absolute minimum at 0, right? And I can also say I have a local minimum at 0, right? So I also have a local f of 0 is a local minimum as well, right? Local min as well. Okay, so when I am defining a local max and local min, I want the function to be defined in an open interval centered at that point. And then it is the largest value. Okay, that's what I want to say. Okay, so that's that. How about the you guys remember the graph of the function f of x equals to absolute value of x? Okay, if I ask you, let's say let's restrict the domain here between -2 and +2. What's the absolute max? Absolute max on this interval is what? And absolute mean. -2. Remember, I'm restricting the domain between -2 and 2, right? So you write this is 0 here, but what's the absolute max? The graph is not going up forever. Now I'm restricting right at -2 and 2. So what's the height of the graph at -2 and 2? It's 2. So that's the absolute.
Okay, there's no local.
Yeah. At 0 you also have a local minimum. Okay, so this is also a local minimum. Am I making sense? Notice that in this case, there is only one absolute maximum value, but the absolute maximum may occur at two different points. Okay? Is everybody okay with that? So even though there is only one absolute maximum value, it may occur at two different points. Okay?
What do you mean by that?
That is, in this case, the graph looks like this, right?
Yeah.
So let's say, let me make my y-axis here. So here is, let's say, 2, right? And here is -2. So what I'm saying is that the absolute maximum value occurred at two different points, right? F of -2 is, so what is the absolute maximum value? It is f of -2, and it is also the same as f of 2, right? So I'm saying the maximum occurs at -2 and +2 as well. So you see, oftentimes I say that there is only one absolute maximum, and students think that what I mean is that absolute maximum occurs at only one point. No, I'm saying there is a one absolute maximum value, which is 2, but it may occur at two different points. Okay. Again, that's a misleading. That's misleading because if I say there could be more than one absolute max, what do I exactly mean? What I mean is that the absolute maximum occurs at more than one point, maybe, but the value is only one, right? There is only one absolute maximum value. I cannot say the absolute maximum is 2 and 4, right? Am I making sense? Where they occur, you have to distinguish that from the value of the function, right? The value of the function and where they occur.
Well, I was just thinking about like a sine graph.
Yeah, so in that case, there are infinitely many places where sine attains the value 1, right? So in that case, the maximum value of sine is 1, okay? But it occurs at infinitely many places, right? Okay, so since we just said that, let's just write that down. The absolute maximum of the function sine x on the entire real number line is 1, and the absolute minimum value of the sine function on this is -1. And you can also see that I have local max and local mean at the points where I have the absolute max and absolute mean, right? Do we know where exactly these maximums occur? The maximum value 1 occurs at the points which are multiples of what? This will be pi over 2, and then you skip 3 pi over 2 because at 3 pi over 2 you have -1, right? So at pi over 2 you get the maximum, 3 pi over 2 you get the minimum, and then 5 pi over 2 you get the maximum again, right? And you keep going like this. Is everybody okay with that? Okay, here is another example. If I have the function f of x, which is absolute value of x squared minus 1, then how many of you remember the graph of this guy? We talked about the graph of this guy before, I think. What's the graph of this guy? Well, you basically draw the graph of the parabola without the absolute value, right? If I don't have the absolute value, it's the graph of x squared minus 1, which is just a parabola, right? So it is like this, yeah. So that's the graph. That's the graph without the absolute value. Now, when you have the absolute value, the negative part that you have to flip it and make it, so you have to reflect it across the x-axis. So this part between -1 and 1, here is -1, here is +1. The part between -1 and 1, you have to flip it. Am I making sense? So now I can erase, let me use a smaller eraser. Okay, so that's the graph of this function. So do I have absolute minimum in this case? So I have local minimum and absolute minimum at what points? At -1 and +1, right? At -1 and +1, I have the local main and the absolute minimum, and I don't have no local max or or absolute max, right? No local max. Well, if there isn't any there isn't any local max and no absolute max in this case, because the graph goes up forever. Is everybody okay with that? Yeah. Oh yes. What am I saying? Local max. Thank you. Thank you. So this is I said it wrong. Local max is at 0. Okay. F of 0. Sorry. So f of 0 is a local max. I don't have any absolute max here. Okay. Everybody is clear? Did you guys see my mistake? Okay. All right. So that's that. Example. If I have the function cosine x, can you tell me where the absolute maximum occurs? So cosine x has local max as well as absolute max on the interval from -infinity to +infinity. On this interval, where do we have the local max or the absolute max values? At what points? Remember, at 0, cosine is 1, right? At pi, -1. At 2 pi, +1, right? So that means you get 1 whenever you have a multiple of 2 pi, and you get -1 whenever you have a odd multiple of pi, right? So at pi, 3 pi, 5 pi, 7 pi, you're always on the negative x-axis, right? So I could say that it has local max at multiples of 2 pi, so 2 pi n. Oops. Or let me just say 2n pi. Here n could be any integer, okay? 0, plus or minus 1 plus or minus 2 dot dot dot. So for any multiple of 2 pi, you get cosine x is 1, and that's the maximum value. Is everybody okay with what I said so far? Everybody's okay? Now, what we want to do is, you see the local max and local mean values. Given a function, we need to find, well, in applications, there are many functions for which we need to find where the maximum value occurs, okay? And the reason is the following. For example, so let's say you are a company, you have a, you make a lot of different products, and you have a profit function. Imagine a profit function. So your goal would be to maximize the profit function, right? So give it, under certain, your manufacturing company, let's say, has certain conditions, right? You have certain conditions like how many products can you produce, right? Because you have limited resources, right? So given the limited resources, how are you going to allocate your resources so that you maximize your profit, right? So it's important in applications to be able to find maximum, minimum values of functions. Minimum because maybe you want to minimize the cost of producing something, right? So, and in order to do that, we need to go over some theory here. So here's the definition. So first of all, we want to know, is one thing sort of intuitively clear to you, that if I have absolute max and absolute mean on a interval, right, it occurs usually at the local max or local min, okay, or at the endpoints, right? The absolute max, absolute mean, right? They occur at the points where you have local max or min, or at the endpoints, right? Now, one thing you want to notice about the local max or local mean is that if I go back to my graph here, can someone give me a characterization of this local max and local mean points? What can you say? What is happening at these points? Yeah. Yeah, that's one way. But any other way of in some sort of calculus concepts? Yeah. One key thing, notice that what is happening here, 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 and here. At all these places, the tangent line is horizontal, right? So the derivative is 0 there. Except for this one, here the derivative, I have a corner point, so the derivative doesn't exist there, right? So local max, local mean values, they occur at these points, right? And so we're going to give them a name. We're going to call them critical points, okay? So here's the definition of a critical point. A critical point, of a function f is a number c in the domain of f, such that either f prime of c exists or f prime of c does not exist. So, yeah.
What about the point where the curve becomes concave up or concave down?
Yeah, I'm going to give you that example in a bit. Yes. Here we're saying a critical point of a function f is some number c if the derivative at c either is 0 or it doesn't exist. Okay, either the derivative at c is 0 or it doesn't exist. Then c is a critical point. Okay. Now notice that if I have a critical point, what may happen? Okay. Here's an example. Suppose that f prime of c is 0 for a function. Okay, so suppose I have a function such that f prime of c is 0. Then how does the graph of f look like near c? Okay, how does the graph of f look like near c? So there are three possibilities that can happen here. One is let's say this point here is the point c f of c. Okay, so that's the point on the graph where that's the point on the graph of f which is c f of c. So this is the point at c. What we are saying is that the derivative at this point is 0, and my question is, how may the graph look like near this point? Well, one possibility, because the tangent line is horizontal here, right? Tangent line is horizontal here. So one possibility is that the graph looks like this, right? Right, that's one possibility. Or maybe, again, I have the point here, c f of c. Another possibility is that the graph looks like this, right? Is that making sense? And this is the point again, c f of c. But there is another possibility that I think you alluded to that, which is I have again the point c f of c, and the possibility is that yes, the tangent line is horizontal here, but then the graph looks like this, like the graph of x cubed. The graph of x cubed at 0, the derivative is 0, right, for the graph x cubed. So the slope at 0 is 0. So even though I have a critical point there, I don't have a local max or a local mean there. Oh, okay. So we're gonna get there pretty soon. Yes. So second derivative will tell us about the concavity. Okay. So we'll get there. So notice that in the first case I have a local mean at c, right? So in this case I have this is a local minimum. I have a local minimum at c. In this case I have a local maximum at c, and in this case I have neither at c, right? You guys see that? So if I have a critical point at a point c, then the graph may look like near c, the graph may look like one of these three pictures. Okay, now what I want to do now is go over a couple of exercises on finding critical points for a given function, and that this is going to be an important question for you in the next exam. So here's an example. Please feel free to get those pastries, okay, if you're hungry. Okay. Let's look at the function f of x, which is given by 1/3 x cubed plus half x squared minus 2x. And the question is find the critical points of f of x. okay, on its domain. Okay, so when I write CT, it means critical. Okay. Okay, so how would I find the critical points of f? Well, we know that critical points of f are the points where the derivative either vanishes or the derivative does not exist. Either vanishes or does not exist. So, well, that means I have to find the derivative first, right? So what's the derivative here? The derivative here is, well, what's the derivative? Can someone tell me what's the derivative? What do I get? X squared plus what? Minus 2. Okay, so I have the derivative here. Now, in order to find the critical points, I have to find out where the derivative vanishes, and I have to find out where the derivative may not exist, right? Where the derivative doesn't exist. So so the first thing I'm going to do is find out. The first thing I need to do is solve for values of x for which the derivative is 0, right? Solve for values of x for which the derivative would be 0. Well, derivative 0 means we know exactly what the derivative is. X squared plus x minus 2 is 0. And can I factor out this x squared plus x minus 1? Can I factor that out? What is that? So what are the values of x? Negative 2 or x is positive 1, right? Okay, so so I obtained two critical points here, right? These are the points where the derivative vanishes. The second thing I have to do is find out where the derivative doesn't exist. So solve for values of x for which f prime of x does not exist. Solve for values of x for which f prime of x does not exist. So what did I get in this case? No solution, right? No solution, right? No. Why? Well, the function that I have is a polynomial function, and the derivative exists everywhere, right? For any value of x, the derivative exists, so I don't have anything there. So what is my final answer then? Final answer then, we have critical points at x equals to negative 2 and x equals to 1. These are the 2 points. These are the 2 critical points. Is everybody okay with what I said? Okay. Are you guys done writing it down? Okay, let me move on to the next example. Suppose that I have the function f of x, and the function f of x looks like 1 over 1 plus x squared, and okay, so in this case again the same question, find the critical points. So in order to find the critical points, what do I have to do? I have to find the derivative first. The derivative in this case is what? Well, there are 2 different ways I could do this. I could either apply the quotient rule, or I can also I can make it 1 plus x squared to the negative 1 and then apply the chain rule, okay? But I'm going to go ahead and use a quotient rule here. So 1 plus x squared squared, and in the numerator I will get the low 1 plus x squared multiplied by the derivative of the numerator is 0 minus 1 times the derivative of the denominator is 2x, and that is equal to negative 2x here divided by 1 plus x squared squared, right? So that's the derivative that we have. So then the first thing I have to do is solve for values of x for which the derivative at x is 0. And so then I can see that the derivative is negative 2x over 1 plus x squared squared. That's going to be 0. If this fraction is 0, then what should be 0? I'm sorry? Yeah, so then the numerator, negative 2x, should be 0, and that implies that x is 0. So we got one critical point here, right? Now the second thing that I have to do is what? Solve for values of x where f prime of x does not exist. Do I have any solution in this case? I potentially would have had solutions here if the denominator vanished at a point, right? But if I look at the derivative formula, the denominator is at least 1, right? Because of the x squared, no matter what x is. So it can never be 0. So in this case, I can say no solution as well. Okay? So what's my final answer? My final answer is I have only one critical point, right? So one critical point at x equals to 0. Are we doing okay with that? Okay, next I have this theorem, and this is called Fermat's theorem. What it says is the following. If f has a local max or a local min at some number c, and if f prime of c exists, then f prime of c must be 0. So what this theorem tells us is that if you have a local max or a local mean at a point, and if the derivative exists there, you are guaranteed that you have that the tangent line is horizontal there. Am I making sense? So if I have a local max at a point and the derivative exists there, then the derivative must be 0 there. Which means what? In other words, what we are saying is that if f has a local max or a local mean at a point c and the derivative exists there, then you have a critical point there, right? Okay. The converse of this does not hold, okay? The converse of Fermat's theorem would be what? The converse would be the following. If the derivative is 0, then I have a local max or a local mean there. Am I making sense? So that converse does not hold because we just saw the example here where we said if I have a point where the derivative vanishes, then I have this third case, right, where the derivative vanishes but I don't have a local max or a local mean there, okay? So the converse of Fermat's theorem is false. That is, if the derivative is 0, it's not necessary to have a local max or a mean there. But if you have a local max or a local mean at a point, then and the derivative exists there, then it has to be a point where the derivative is 0. Okay. Okay. So another way of saying this would be that the local max and local mean values may only occur at the critical points. Okay. Am I making sense? So so this also says this. So an implication of this is that local max and local mean may only occur at critical points only. Okay. So if you want to find, let's say all the local max and local mean values of a function, what should be our strategy? Well, our strategy should be we find all the critical points, and if we find all the critical points, those are the possible locations where the local max mean may occur. But not all of them will be the points where local max mean occur, right? So then once we find the critical points, then we have to look at each point and see whether each one is a local max or a local mean. Am I making sense? Is it clear what I'm saying here? So the local max, local mean may occur only at the critical points. Okay, local max, local mean may occur only at the critical points. So if I want to know all the local max and local mean values of a function, then I should be finding all the critical points first, and those are the only possible locations for the local max and local mean values. But not all of them. All of them may not be. All the critical points may not be locations of local max and local mean, but they are the only possibilities. Okay. The next theorem is called the extreme value theorem. Extreme value theorem. Okay, so the extreme value theorem says the following. If f is continuous on a closed bounded interval from a to b, then there exists C comma D inside of this interval such that f of C is larger than f of x for all x in AB, and f of D is less than f of x for all x in AB. So in other words, what I'm saying is that if f is continuous on a closed bounded interval, then f must attain an absolute maximum value and f must attain an absolute minimum value. Is that making sense? Is everybody okay with that? So this is saying that if f is continuous on a closed, we saw that we saw examples where f doesn't have an absolute maximum or an absolute minimum, right? So what we are saying here is that if f is continuous on a closed bounded interval, then you're guaranteed that f attains a absolute max and it attains an absolute min. Okay. Now my question to you: suppose that I have a function which is continuous on a closed bounded interval, and if I ask you to find the absolute maximum and absolute minimum values of f, how would you go about it? How would you go about finding? Again, I have a continuous function on a closed bounded interval, let's say between 1 and 2, and if I ask you to find the absolute maximum value of f and the absolute minimum value of f, right? How would you find it? Given that you don't know the graph. I mean, if you have the graph in front of you, you can just say that, hey, this is the one. How would you go about it? Well, what are the possible points where the absolute max and absolute mean may occur? What was that? No, I mean in general, what are the points where the absolute max and absolute mean may occur? Well, think about the graph, right? It may occur at the end points, right? Because let's say I have the f of b is the largest value, right? It can happen. If I have an increasing function, for example, that can happen. Well, what would be the other possibilities? If the absolute maximum value occurs, if the absolute maximum value occurs at a point which is not an endpoint, if you have the absolute maximum at a point which is not one of the endpoints, then that absolute maximum will also be a local maximum, right? Well, if it is a local maximum, then the derivative would either be 0 or, well, if I have a local maximum, then by Fermat's theorem, I know that it's got to be a critical point, right? Am I making sense? So once again, what I'm saying is that I have for the absolute maximum value, right? I might have a possibility that the absolute maximum value occurs at b, right? At one of the endpoints. So the absolute max or absolute mean may occur at one of the endpoints, right? This is the largest value. The other possibility is that at this point A and at this point B, let's say, the absolute maximum, let's say, does not occur at any of these points. The absolute maximum does not occur at any of these 2 points. Let's say it occurs at a different point, C, right? So let's say the absolute maximum occurs here, right? So the one possibility for the graph is like, let's say this, right? So if I have a point in between A and B where I have the absolute maximum, that absolute maximum will also be a local maximum, right? And Fermat's theorem says either if the derivative exists there, then it's got to be a point where the derivative vanishes, or the derivative doesn't exist, right? Maybe it has a corner point, right? Either way, I have a critical point there. Am I making sense? So if you have the absolute maximum in between A and B, then I have a critical point there. Okay? My point is so if I have a continuous function on a closed bounded interval, the absolute maximum and absolute minimum may only occur at the endpoints or at a critical point. Okay, there are no other possibilities, okay? The absolute minimum and the absolute maximum value of a function, of a continuous function on a closed bounded interval, may only occur at the endpoints or at a critical point. So if I want to find the absolute max, absolute mean of f on a closed bounded interval, what should I do? I find out all the critical points, and I then evaluate the function f at the critical points and at the endpoints, and I know those are the only possibilities for the absolute max and absolute min, and I can just pick out which one is the maximum. Am I making sense? So that's what I'm going to do in the next example. Let's say I want to find the absolute maximum and absolute minimum of the function f of x, which is x cubed minus 3x squared plus 1 on the interval from -½ and 4. So on this interval, I want to find the absolute max and absolute min. Now, the extreme value theorem says what? If I have a continuous function on a closed bounded interval, which we have, then I am guaranteed that there is an absolute max and there is an absolute min, right? Extreme value theorem says, guarantees the existence of the absolute max and absolute min. We just have to find them. Well, in order to find them, we know that the absolute max min may only occur at the endpoints of the interval or at a critical point. So the first thing we do is find out the critical points. How do we find the critical points? Well, we saw them. We find the derivative, which would be 3x squared minus what? 6x, right? Everybody's okay? And then we solve f prime of x is 0. Well, that tells me that 3x squared minus 6x is 0, and which tells me that if I factor out 3x, I get x minus a 2 here, 0. And so that tells me that x is either 0 or x is 2. Are we okay with that? Are these the only critical points here? Well, yeah, because if I try to know points, right? No x such that f prime of x does not exist, right? Because the derivative exists everywhere. So the only critical points I have are the points 0 and 2. So now, in order to identify the absolute maximum and minimum, I make a table of values, okay? So here's my x value and f of x value. My x values would be the endpoints and the critical points. So I have the value -½, I have the value 4, these are the end values, end points of the interval, and then the critical points are 0 and 2, right? What I have to do is find out the value of f at each of these points. So remember what was f of x? X cubed minus 3x squared plus 1. So what is, let me do the harder ones and you do the easier ones. F of 0 is 1. Okay. F of 2 is, f of 2 would be 8 minus, f of 2 would be 8 minus 12, which would be minus 4 plus 1, which would be minus 3, right? F of 4 would be 4 cubed, which is 64. 4 squared is 16 times 3, so that's 48. And 64 minus 48 is what? And plus 1? 17. And what is f of -½ If you plug in -½ you get negative 1/8, negative 1/8 minus 3/4 and plus 1, right? So what is that? That's going to be, what's that? Let me see. So this would be 8 negative 1 minus 6 plus 8. Yes, 1/8. So you get 1/8 if you plug in negative half. Okay, so we know that absolute max and mean will be one of this. Okay, so what is the absolute maximum value? 17. So this will be the absolute maximum value. So here I have the absolute maximum value is 17, occurs at the point 4, and what's the minimum? Absolute minimum. Absolute minimum is negative 3. It occurs at the point 2. Am I making sense there? How much time did I spend on this problem? Was that? Yeah, all the discussions that I did before this, I spent enough time on this, which means that I'm probably going to ask this problem on the exam, right? Okay, so in this example that I just gave, this is going to be an important example for your next exam. Okay? Any questions on this example? If you have any questions, please go ahead and feel free to ask questions.
So,
yeah.
Can we go back to that?
Go back up?
Go back to the end.
Toward the end? Yeah.
So, your local mins and local max.
Okay, so all I'm saying here is that we know that the function is continuous on the closed bounded interval. So extreme value theorem guarantees I have a local max and a local min.
Oh, we're just discussing extreme value.
Yeah.
Oh, okay.
We know that there is an absolute max and absolute min, and so we need to find them. And we discussed before that they can only occur at the critical points or at the end points. And so that's why we found the critical points and the end points, and we looked at the values of f and picked out the maximum and min. Okay. If you wanna, we are going to talk about how to find local max and local min. We're going to see examples like that pretty soon. Maybe not today. But in this case, if you think about it, 0 and 2, those are the critical points, right? Those are the 2 points where the derivative vanishes, right? So those are the candidates for local max and local min. But do I have a local max and local min at those 2 points? There is no guarantee because of the third case, right? Even if the derivative vanishes at a point, doesn't mean that I have doesn't really mean that I have a local max there or a local min, right? Because it may look like the graph of x cubed. Okay. So, but we are going to later on see examples how to identify local max and local min. So that's coming pretty soon. Is everybody doing okay with what I said so far? Okay. Should we do another example or? Oh, I know what. I want to do one more example that I forgot to do. Because this example is finding critical points, but it has some algebra that I think I should be doing at least one of those. So here's this example. Let's say I have the function f of x, which is x to the power 2/3 multiplied with 6 minus x to the 1/3. And the question is find critical points of f of x. Can someone tell me what's the domain of f? You have 30 seconds. What's the domain of f? Everywhere. Well, if you even if you didn't know what to answer, you should have said everything, just to check if that's correct. Yeah. With x, we have the cubic root, right? But the cubic root is defined for even if x is negative. So this is defined for any x. Okay. So the domain is all real numbers. I want to find the critical point. So what's the first thing I need to do? I need to find the derivative, right? So what's the derivative in this case? I have to apply the product rule, right? So this is one factor, this is the other factor. So the derivative of the first factor is what? 2/3 x to the 2/3 minus 1, right? Multiplied by the second factor plus the fixed factor as it is, multiplied by the derivative of the second factor. What's the derivative of the second factor? What's the derivative of the second factor? 1/3 6 minus x to the 1/3 minus 1 multiplied with negative 1, right? Very good. Okay, so this is going to be then 2/3 x to the negative 1/3 6 minus x to the 1/3 plus x to the 2/3. I have a negative and then I have a third. I'm going to write that first. X to the 2/3 6 minus x to the negative 2/3, right? Okay, now I have to find out where this derivative is 0, right? I have to find that out. In order to do that, I have to simplify this first. So how may I simplify this? How would I try and simplify this? You can't just cube everything because you're changing the value, right? So there are a couple of different ways of going about it. One way would be, first of all, I am going to rewrite this x to the negative 1/3 as, so I'm going to write it as 2 times 6 minus x to the 1/3, okay, divided by 3 times x to the 1/3. Can I do that? Because I have x to the negative 1/3, so that would be 1 over x to the positive 1/3. So I could rewrite the first term this way. The second term I could say is 3 in the bottom, x to the 2/3 here, and then I have 6 minus x to the 2/3. Okay, so this is not simplified enough yet, okay? So that's what you're trying to say. It's not simplified enough yet. So what I'm going to do is add the fractions, and what's the common denominator? What's the common denominator? Well, 3 times x to the 1/3. I'm not going to take the other 3 here because 3 is already there. So the other factor would be 6 minus x to the 2/3. So this would be the common denominator, right? You agree with that? Okay. So then what? In the numerator, what do I have? I have 2 times 6 minus x to the 1/3, and that will be multiplied by what? it will be multiplied with only 6 minus x to the 2/3, right? So what you do is, this is the common denominator, right? So you divide the common denominator by this. What do you get? 6 minus x to the 2/3, and that's going to be multiplied with this guy. Did that make sense?
2 times 6 to the 3rd.
So this will be multiplied with 6 minus x to the 2/3. Minus, what's going to happen here? When I divide the common denominator by this, what's going to remain? When you divide the common denominator by this, by the second denominator, right? The denominator in the second fraction, what did you get? X to the 1/3, right? So you get x to the 2/3 there already, multiplied by x to the 1/3. Everybody's okay with that? Well, what do I have now? Notice that I have 2 times 6 minus x, right? Because 1/3 plus 2/3 is 1. Minus, I have simply x here, right? So I have 3 times x to the 1/3, and I have 6 minus x to the 2/3. Everybody's okay? Now what do I have in the numerator now? I have 12. I have 12 minus 2x minus x, so that will be 12 minus 3x, right? And I have here 3x to the 1/3 times 6 minus x to the 2/3. Okay? So this is simplified enough, okay? So this is the derivative. Now I have to find where the derivative is 0. Well, I don't have to do much work. Where is the derivative 0? F prime of x is 0 if what? If the numerator is 0, right? And the numerator 0 is when? 0, or it means that x is 4, right? X is 4. And f prime of x does not exist where? If x is 0 or 6, right? The derivative would not exist. The derivative would not exist if x is 0 or 6. So the critical points are this, this, and this. Is everybody okay with that? Everybody's good? Okay, why don't you guys take a break? I'm going to give you the exam at 11:30. Feel free to take some pastries from there.